Please be seated. Gary, please be seated. Okay, so we reached the last session of David Fest, and we have two lecturers, which are good friends and colleagues of David, Francois Englert and Eliezer Rabinovich. And what's common to Francois and Eliezer, that both are
common?
frequent visitors to this country. And we are always happy to see them.
To see him. Yeah.
So, Francois. The first lecture is by Francois Englert and on the quantum fate of horizon and the fuzzball hypothesis.
Okay, first a few words. I have to explain something about me, and that, since relatively lately, I always had the impression that people that I knew, I appreciated, and things like this, they were older than me. I always had that impression a very long time, and I tried to understand why. And I did not succeed, but I had this. Well, the closest to something that probably is partially right is that, as a Jew hidden from the Nazis during the war, I had no relation, it was better, with other children. So I never knew the other children. The only person I saw was the adult, some adult. And the adults were, by definition, scaring, right? So in addition, I always find these people scary, right? So it's a little bit complicated to behave like a usual normal person here. And actually, the first time I met you, I don't know if it's in Cargés or if it was in what's called Yugoslavia at that time. It was there. And I was extremely impressed by his intelligence, his view on everything, which was wonderful, but at the same time, I must confess I was a bit scared. So I don't know, it's scared for what, I don't know exactly, but all this intelligence put into a big man with large moving hands. I remember I was a little bit not at ease with that with you, but well, okay. Now, after that I start understanding that I was wrong with all my view of adults, because first I was a bit too much invited to conference of people who were celebrating their 60 years birthday or late. They were incredibly young. I mean, I thought they were already 80 or something like that. So you have to understand that this is an impression I had completely independent of the way they looked. And, but of course, this cured me a little bit. And so finally, I realized that David, which I met a little bit more later in my life, when I was a little bit more sane, let's say, in that point of view, and that he was not only the brilliant and one of the best physicists we had in this century, in the last one also, of course, and but that he is a very gentle man. He is very gentle, and therefore I have no problem now to wish you all years of happiness to come, and all realization in whatever domain you decide to be realized. Okay? Okay, so now I'm trying to go to physics, but I want to say one thing. This is Sasha Belavin, where it is made. Sasha Poliak. Oh, there are too many Sashas, right? Okay, Sasha. he said something very nice about what happens at 50, that you fall into the black hole. Now that I'm a little more at ease with age, I can tell you that of course nothing happens when you cross the horizon, but when you reach 80, you are feeling that you are neighboring the singularity. You see, so that is something which is not always pleasant. So, now, what I want to do is, of course, being aware of this age, I'm not going to have the chutzpah to try to make a theory of gravity, right? There are things alone, but it's not that. But I would like to try to say that there may be a possibility to understand if there are things in gravity, in quantum gravity, that manifest themselves very early in gravity and at the lowest possible level of quantizing gravity, no matter what. We'll do a phenomenologic view on that, and you will see what I do. So let me start. I will talk about the back reaction, and the rest will be clear when I talk about it. Okay, let's suppose for 1 second that gravity would be an ordinary field, and that we want to do something which is natural in the context of gravity, and namely the amplitude for finding a given state on a hypersurface from knowing another given surface functional integral. So this is just a scalar product of two states, Fi, in the Heisenberg representation, which would be just a functional integral. And of course, I'm dropping any problem with measures or anything like that. And the intermediate surfaces define your choice of time. And well, you can take then even simpler example in which I will suppose that the field is just a classical field obeying some equation of motions and one quantum field, which I will take, and I think that would probably be all of it. So the fictitious action, or the action which is there, would then be separated in two, namely a one, which is defined when the quantum field is 0, and the remaining part. And so this obviously is not correct, but we may imagine, I think, with some decent probability that it's correct, that somehow there exists in whatever theory, be it string theory, be it huge type of algebras or whatever, that something like a stationary point should exist. And therefore, and not only should exist, but in the vicinity of stationary point, you would expect, at least I would expect, that you should be able to describe that biometric. So what I'm going to do is to take that thing here, but use it only at stationary states. That I think is probably safe at that moment for many things, and I hope. So the functional integral which we write, and that's why I don't have to make things complicated, are only valid in the vicinity of stationary states. Now, let's do that. So we write mu nu as some background that we don't know in principle, plus some fluctuation around, where the background will be defined by the stationary state. So you have this two, so you have the two terms at order 0, out of which you can compute the 0 order term, let's say the term in the fictitious background, in the background that we don't yet know, plus the first order terms. Fine. Now we want to annihilate them. We have to be a little bit careful because we have already an integration on the quantum field here at the 0 order in gravity. So when we write here for the S of phi, the one which exists when phi is present, we have to, in order to get a 1 here, we have to divide by the quantity that we have factored before. And therefore, what you do here, if I like, I can write to first order, of course. This as an exponential is a bit more nice. It doesn't change anything, of course, because we're looking first order. This is what you get. And then you see very well that this is something that you would expect, but there is a correction which will turn out to be important. Namely, it's the matrix element of T mu nu between the initial and the final state divided by the scalar product of f of I. This quantity is known particularly to many people in Tel Aviv. I think not so many are here. But these are very known because that's called the weak value, and which has been very intensively studied by Aronoff in the context of measuring and making approximate measurements and things like this. And but here, and these are the thing, and it's called the weak value. But this quantity for us is just something that comes in the right-hand side of the classical equation of gravity when we write it between an initial and final state. By classical, I mean the equation of the stationary state. Now, originally, as I said, these weak values were used to describe rare events, but here the situation is different. And we'll see that this, and we see that as far as the amplitude is concerned, this is what drives correctly the back reaction to first order of gravity, where the background is defined self-consistently in principle by the equation which is there. Which is, Yes, it contains an imaginary part, I will say so. In fact, the metric which is there could be complex, right? So it's not the usual type of background when it has an imaginary part, but you can still define a stationary point. So this is what you get. Now let's see a little bit what are the properties of this weak value. You see, sometimes it's a bit better to see it in the Schrödinger representation because there you understand the state at time t0 and the final state, and this is of course the same thing, except that you see now that what you are doing here is writing essentially the S matrix, if you go to sufficiently large time, if you wish, between the initial and final state, and trying to get information about an operator in the region between the S matrix. You ask what happened to the operator when you know the initial and the final state, or if you want, you know an inclusive S matrix element. So, what is the relation with that with the more conventional thing, which is very often written as the back reaction, but that's incorrect. It's the, you just see by multiplying this by the complex conjugate and by putting here IF, that if I take the probability of finding those things here, I find by summing the probability of the weak value is just the average expectation value, which is real. Right? So you have that. And except for that, what can do if we can also make a partial post-selection. And I take the example of the black hole background without any back reaction at all. It is the standard result, the standard Penrose diagram for a collapsing shell. And we are going to focus on what happened in the region where we don't have any problem with unitarity, which is defined by the initial Cauchy surface, which is chi minus, and the final, which is the one where we have H, where the space, the final state is the product of the horizon and sky plus. Now, I remind you that, and that will come later, that to get the Hawking radiation, you never have to go in that order outside the horizon. Everything can be defined in that unitary perspective, and the whole thing that happens is that you get a thermal distribution because you take the trace of the horizon, and that's all. So everything is unitary for the moment. You don't have any problem with that. And so the question is, if we make a partial post-selection, for instance, the final state here, a post-selection such that the scalar product is never zero and that it builds a complete set of states. That is what we want. For instance, if you have the Hawking radiation, you take, for instance, all the states of the Hawking radiation that satisfies these axioms. So you take the weak value, and how do you make a partial post-selection? It's immediately clear if you write this as a trace of this way, which is exactly the same thing. You see that you just have to put, instead of the trace of one final state, you put a trace times the projection operator on H2, because you don't know anything on H2. That's actually equivalent to define a single final state, because writing this by the cyclic inverse of the trace, I can write it like this. And so this is just simply a final state, which is the product of this times the EPR conjugate of this on the horizon, because this is defined on the horizon. And this quantity, the denominator which is there, is just the norm of that state, because the EPR conjugate will generally not be norm to 1 if I is norm to 1. And so you have that, and you see immediately the probability is the square of this divided by its norm, so it's the same thing as this, because that's also its norm. So we have the same relation as previously. If we sum on all the states on Sky Plus, together with the EPR conjugate, for the weak value, we can get the average expectation value. And where the probability suitably normalized is this. And summing of all the states, you again get the expectation value, which is real. Now, if you have no post-selection, justify the initial state, then the same expression can be written by taking the trace over everything, of course, which is just by itself the expectation value. So what happens in this is that for each of these choice of final state, you have different backgrounds. And the backgrounds are given by the solution which is there. This is the, and I write it T mu weak, where T mu weak underline depends on what type of post-selection or final S matrix element that you have, which for simply a post-selection, or a post-selection is what was defined as the weak value. If it's a partial post-selection, it's the same, but you have to take as a final state the product of what happens on H times the EPR conjugate. And if you make no post-selection, then you just get the average value. The question, of course, is whether these states, which is the first effect of the back reaction, if these effects are the same or very different. This is the point of the discussion. And so this is going from exclusive to inclusive amplitude to the language of the S matrix, and it goes from that equation to exclusive to inclusive background. What is the relation between them? First, we can see immediately from here that the inclusive background, the one defined by the no post-selection can be viewed as an average over all the inclusive or semi-inclusive backgrounds, because to get this thing from a weak value, you always have to multiply by a probability. And so you have to use, in whatever approximation you do, you have to use an average of all these exclusive background to get the inclusive one. That will play, of course, an important role in what I want to say. Now, I want to illustrate that, and a little bit more perhaps, in the case of the simplest case for me, which is the black hole. In that case, in that thing. So this is, as I said, the incipient black hole, and just remind you that there's no problem of unitarity as long as you remain into that domain which is shaded in blue here. And now, we can make a very simple example to see what happens. First, just usual two-dimensional approximation that you get by taking the metric with dropping that term, and that's something like essentially the S wave if you neglect the relativistic background, the relativistic barrier for this case. And but so you can do that. That, of course, you can solve exactly. It's not a problem. You know how TUV is from the trace anomaly, and you see that it has a 0 on the horizon. You see that the TVV, which is there, is given by an expression obtained by integrating the equation of motion. So there's an integration function actually here, which depends on V, and which normally you put equal to 0 because you start, let's say, from pure Minkowski space, and there's no flux supposed to go there. TUU, you have to add to this as a constant the thing that doesn't go to 0 at large R, namely the Hawking radiation. That can be, of course, computed very trivially in 2 dimensions, and the computation of this thing is just 1 over m squared over 48 pi. You can show that very easily, and that is what you get in the collapse. Now, you could also put, for the moment, just as a game, TUU equal to 0, and that is nothing else than what's called the Buller vacuum, namely the one, what is this? No, this is okay.
Yeah, okay.
Okay. Yeah, maybe I should not lean on this thing. Right. So the Buller vacuum when TU is equal to 0. Now, close to the horizon, these things have the following behavior. The TUV has a single 0, the TUU has a double 0 close to the horizon, the TVV has a constant on the horizon, which is there. So, if you want to characterize the Unruh on the Buller vacuum here, you just can characterize in a coordinate independent way. You can form that scalar, and this now you see that this is welcome because this thing has a double pole, and that double pole kills the double pole of the TUU and the product of the double pole from the trace anomaly. So this is something which is a pure number, which you can compute is there. If you try to say, well, so I put here the index 2 because that's a computation in 2 dimensions. In 4 dimensions, I will not make an exact computation, but you can guess the order of magnitude very easily, because just the 2 dimensions you have to divide by 4 per m squared for the S wave, and so you get 1 over m8, and you can see that this, in fact, sticks if you take all the effects. At least that has been shown by Candelas a long time ago. And the Böhler vacuum now clearly is divergent because we have this double pole, but it's not cancelled by zeros because the TVV doesn't go to zero on the thing. So you can write now in that approximation the exclusive equation, the inclusive equation of motion, which is the one in which the source is the expectation value, and it's here, and that clearly is totally negligible, as we all know. And so, according to Sasha, we know that we crossed this without any problem. I just mentioned the problem after 80 years. But so this is okay. And so with no post-election, the back reaction rate is small. The classical rate is not sensitive to such back reaction. Now make a partial post-selection. I take a state psi and part of a complete set, the way I defined it, and the T mu nu weak is that expression here, where the denominator is the scalar product of the I times the final state, which is the product of the state phi, which is post-selected on AJ, times this thing, which is the EPR conjugate of the horizon. And now let's see what this is. In order to do that, it's convenient first to go again to 2-dimension. And in 2-dimension, what you can do is to take, for instance, the normal ordering. I'm not going to write explicitly the T mu nu, but clearly you can normal order, and then you have, of course, a constant, which you have normally to renormalize, which was done for you automatically by the equation of motion, which I wrote. But normally this is the quantity. This is supposed to be the renormalized T mu nu. And we can now expand this into this expression where the T mu nu 2 with 2 dots is just the value containing 2 creation operator on out states. And that again, with respect of this acting on an in state, from a Bogoliubov transformation, you can always write this in terms of operating acting on in state. So you can do that, and you see that one way to see that is that this is equal to that up to, again, an integration constant acting on I as an operator in principle, and you have that equation. Now it's very easy to see what this C is, because you take the scalar product with the final vacuum, and then this is 0 because this contains only creation operator, so this vanishes, and so this is just a quantity I will write in a moment, which is this. This is the constant, right? Which is only the these two things together are just the expectation value of T mu. They are just the weak value of T mu nu for a final state which would contain no photon. So this has to be the Böhler vacuum, and that you can find. You can check that by explicit computation if you want, but that's nearly obvious. So you see that what happened, and that's the essential of the problem essentially, is that this term I call the radiation term, because this is creation of pairs, right? Only that you can write the TUU, the radiation, essentially the Hawking radiation when you are close to the horizon, you can write it on a Böhler vacuum, which is essentially a divergent operation, times this object. In other words, you have you can always write it as radiation on the Böhler vacuum, which is of course singular, and we'll look at singularity in a moment. Therefore, you see that it's going to be very hard to get rid of the singularity, because any mistake in the computation that would take that this quantity is not the Hawking radiation exactly at the final state will generically not be able to kill the Boller singularity, which is the first two terms. And that I will make a little bit more explicit, but you can already see the origin of the problem. And so this is regular on the horizon, that's the Unruh vacuum. This, together with that, is singular on the horizon, it's a Boller vacuum. And this essentially is the Hawking radiation contribution of the state phi on top of the Boller vacuum. This is quite general in 2 dimension. And to remember you, the vacuum term for the expectation value is this number. If you add this number, which is a constant, you just kill this thing. Oh, I again did something wrong here. And therefore this quantity leads to a divergent thing, because it was the Hawking radiation that killed the divergence. So you take things. So the radiation term here can now be computed in the 2-dimensional case, actually exactly once you choose the state psi. And if you take, for instance, psi and expand it into another complete set of states which are energy state, you easily derive the formula here, which I've written by discretizing, so the time is a cutoff which disappeared in the continuous limit. And so this is divergent on the horizon, except in very particular case, where this thing is essential, where it's equal essentially to the expectation of the energy, which is the case, for instance, if all the alphas are taken equal to 1. But even in that case, you're going to get a problem with the second term, because when the numerator has also non-diagonal term, which are oscillatory terms, and these give oscillatory divergences when you approach the horizon. So let's try to characterize this again in an invariant way, and then go a little bit more to 4 dimension. The quantity which is generally used for this is what's called the proper distance to the Hawking radiation, which is that quantity which is easily evaluated here, and which is just the simple quantity r minus 2m delta squared, the coordinate distance, divided by, no, I'm sorry, divided, no, why did I do that? No, the proper distance here, it's the proper distance squared, it's distance squared, as you see, divided not only by m, but by m squared, because this is going to go, when delta is equal to 1, what's the meaning is when you reach an invariant distance which is of the order of Planck scale, because it's easy to see that that quantity is the same as the value of the local Hawking temperature. So when delta is equal to 1, it means that you are at the Planck distance of the horizon. So what you see is that the value of this coordinate invariant in 2 dimension is just 1 over delta 4, because 1 delta squared for each t mu nu, which is here. So the weak value of t mu nu squared, the coordinate independent, diverges as 1 over the local temperature in the when you approach the horizon and have divergent oscillation in general for generic states when you approach the horizon. So you can now try to do that in 4 dimension, but here you have to be careful. When you do that in 4 dimension, first thing would be to derive this, to take a 1 over m4 as previously, 1 over m squared for each converting the T mu nu into 4 dimension. That is 1 over delta 4 and 4. But then you have to realize, and you can show that in many different ways, that in this case, where we don't have any compensation going on, and then we have every mode essentially which can go to some which is close to the horizon. We can define that the number of modes at a different delta which form essentially a heat bath there is of the order, you can compute that just by looking at the potential, the relativistic barrier potential is then 4 over delta 4. So the result is a divergence that goes 1 over delta 8. So outside the star, actually inside the star also, if I remember correctly, this T squared weak diverges like 1 over delta 8. So the curvature square that we had becomes incredibly large. Now we have to interpret that, right? So the back reaction of generic weak values appears to be prohibitively large at when you approach the horizon. And what happens, of course, is that despite the fact that the background is an average, the whole thing comes from making a quantum sum on the final state, which is essentially an interference process. So all these divergences which are there kill themselves by a interference process when you go to the expectation value. In other words, when you go to the background that you like, namely the one that you cross without any problem. This one you may have problem, right? And this is the one that you have for practically every weak value. In other words, for very for all, essentially nearly all exclusive amplitudes. And of course, that means also that the whole computation is incorrect because we did the first order. So whatever you want to do more, you better have a theory of quantum gravity to do, but nevertheless, you can already guess that something is happening here. Of course, you cannot prove it, but the intuition that one gets is that there is a problem with the horizon in quantum theory. Namely, what I say is that it looks as if, but it's not a proof at that level, that horizons catalyzes weak values, which normally have very small effect, from rare events to generic ones. For not that every weak value is the same, but they are all badly behaved, essentially, when you approach to the horizon and give something which makes that the first order approximation is essentially invalid, and that you may expect that something happened. And if it's invalid, the only way, in my opinion, it can be invalid is that the horizon is becoming a material object, whether it's being a singularity or not, in the inclusive amplitude, in the inclusive backgrounds. They are wrong. Something is happening on the horizon which cancels by interference on the exclusive one, although the exclusive background is not a quantum superposition of the background, but a average of this. So that's rather a little bit subtle, but I think that's what happens. Of course, we can find counter-arguments, but I'll leave that to you. And so what I'm saying is the event horizon become quantum material object for exclusive amplitude. That is what I would expect. It's not, there are arguments in which you can try to destroy this, of course, And this is not 100% proof, but nevertheless, I think it's a strong indication. And the classical event horizon arises by averaging the exclusive background, not by summing them, by averaging them with a kind of statistical thing. And so that essentially means that the classical event horizon has a thermodynamic entropy, not something that is related to anything else in that sense. It's a thing, and therefore probably the whole classical limit of quantum gravity, if this thing is wrong, must be viewed as an average and not as a, I would say, as a saddle point of a quantum theory. It should be viewed as an average, and therefore something like a discretization of it or whatever thing has to come out of the theory, has to, quotation mark, right, if this is right, has to come out for this thing. And this is reminiscent of what happens in the things that you do, for instance, in ADS-CFT, whatever, when you study the fuzzball. Because all these geometry, which are in principle complex, are essentially completely real when you are out of a Planckian distance from the horizon. So they're all the same, but they turn into quantum effect, which in this, if this approximation catches the real thing, which has no horizon but some quantum type of structure when you write the thing. That's what you would expect. In addition, you know that the classical horizon from this should appear in averaging these small time geometries. That is what I would have expected from this. Of course, the argument is a little bit shaky at quantically because it's based on first order perturbation theory, which is a little bit too much. Thank you.
Questions, remarks?
You kept talking about post-selection. So there's a proposal.
If you, I'm sorry, I didn't hear. My ears are not what they used to be.
So you're discussing quantum post-selection. So Gary and Juan Maldacena had a proposal for trying to resolve the black hole information paradox using post-selection. So I'm just curious if you thought about this or you have any comments as to what you're thinking is the same or different.
Yeah, I by definition, by here, I wanted to avoid a discussion of this because this is even more problematic than this, right? The point that you get in this is that clearly, I don't know how to answer this, but clearly here it would seem that if you really stick yourself to individual state, you never have to even to pose the problem of the singularity because you will not get, well, you could cross the horizon, that I don't know. At this level it's not sufficient to decide whether you close or not. The horizon is material, so if it's a barrier and you can't, if it's the extremity of space for the non, then of course, but that becomes conjectural in this point of view, of course. Not enough in a well-defined theory to answer that question in definite ways. But what I think should happen if this conjecture is right, that the full space that you get, the same thing that the horizon becomes an average, the classical theory must also become an average. So everything that you have to do is when maybe you can still quantize that, but you have to be careful because you are quantizing something like a discrete space, and whatever that means for the singularity, I don't know, but I would expect that if this is right, finally, there should not be singularities in the black hole.
Gary?
there are no further questions, let's say Francois Englert.